computers have two very important parts. One is hardware and another is software. A software consists of a number of programs, and a program actually consists of algorithms and data. What we're going to see in today's episode is what is meant by algorithms. Algorithm is a series of steps that we take to fulfill any action. For instance, this shows an algorithm for making tea. There's a series of steps. There's a number of steps that we see. Begin and end are the delimiters, and there are 9 steps that we have shown here. Boil water, put tea powder in a kettle, pour boiled water in the kettle, wait for 3 minutes, boil milk, put boiled milk in a cup, add sugar to the cup, empty the kettle in the cup, stir the cup with a spoon. I'm sure that a number of people will have different procedures and processes by which you can make tea. And some tea will probably taste better than the other. But this is one of the ways in which you can make tea. Now, these are called as steps in an algorithm. As steps carried out one after another is what forms an algorithm. Let's now take the same example shown in the form of a flowchart. Flowchart is nothing but the steps shown in graphical fashion. Normally you use in graphical fashion rectangles, and for conditions, the diamonds. We will see these shapes in the slides that we're going to see later. In the same algorithm has been shown here in the form of a flowchart, and as you will see, we begin, then we boil water, we put tea powder in the kettle, and so on and so forth, until in the end we stir the cup with a spoon, and then the tea is ready for us to drink. Let's take another example of an algorithm. In fact, if you look at the first slide again, boil water is the first step in making tea. Now, boil water itself consists of multiple steps, and that's what is the beauty of algorithms. Algorithms have various levels, and each level defines a particular detail at which you give various steps. For instance, making tea consists of multiple steps, and in one of the steps is boil water. Boil water in turn consists of multiple further steps, and that's what we're going to see now. What does boil water mean? Boil water means take a utensil, take the utensil to the water tap, open the tap, fill the utensil with water, close the tap, put the utensil on the gas or in the oven, start the gas or the oven, wait until the water boils, and switch off the gas or the oven. Now all these steps together means boiling water. So making tea consists of several steps. One of these is boiling water, and boiling water consists of several steps. Now if you take one step of boiling water, like take a utensil, that also could be broken into several steps. Now this is the whole beauty. In fact, in our lives, when there's very small instructions, for instance, crawling or walking, and walking a step, turning our head to the left, turning our head to the right, or looking straight, looking up, and so on and so forth. These are very small micro instructions. As we learn, what does learning mean? Learning actually means combining multiple of these instructions and forming what we call as macro instructions or higher level instructions in our head. And as we learn more and more, essentially the level of the language or the level of the instruction which we understand actually goes on increasing. For instance, when we actually tell somebody to bring something, let's say bring a soap from the shop, we can just instruct that person to bring a particular soap from the shop. We don't need to tell that person to lift your left leg and then put it across for one foot, then lift the right leg, and so on and so forth. If we had to do that, then we had to give very detailed micro instructions of going straight and turning left and going down and going to the shop and taking the note out and then giving it to the shopkeeper and so on and so forth. Instead, one instruction of get the soap combines or compresses, so to say, all these instructions that we are saying. Because we have learned what it means to bring a soap, we execute that instruction in detail, while we can take the instruction only as a macro instruction, and that is that of bringing or fetching a soap. So that's the whole point. When we learn in our lives, we're adding levels of instructions to ourselves, which means that we don't need to be given very detailed instructions anymore. Let's take another example. As we know, we do not execute all the instructions only one after another. In fact, there are quite a few instructions which we execute depending upon certain conditions. For instance, when we tell a person to bring a vegetable only if the vegetable costs 10 rupees or less. What we are saying in short is not giving an instruction which is unconditional, but we are putting forward a condition. What we are saying is only do this if a specific condition is met, and therefore these are called as conditions. And in order to execute these conditional statements, there are multiple constructs which are used in an algorithm. For instance, there is a construct called selection. What does selection mean? Selection means if so and so happens, then you do so and so. And that is shown in this slide. For instance, if it is hot, then switch on the fan. And I have shown in the algorithm end if. We will talk about the significance of end if a little later. But what this instruction shows is that if it is hot, I'm instructing somebody to switch on the fan, which essentially means that if it is not hot, don't switch on the fan. And this is what we mean by selection. So we're selecting an action. Now let us talk about, let's say, another example. If the guest wants tea, then make tea and offer biscuits. Now there is a very interesting problem here. There's an interesting challenge here. If you look at the algorithm which is shown at the top of this slide, you will see that if the guests want tea, then you are giving the guest tea, but you are not very sure about whether you are offering the biscuits if only the guest wants tea or regardless. You are not sure whether you are offering the tea regardless of whether the guest wants tea or not. And that's why end if is a statement which denotes where the reign of the if statement ends. In all the programming languages such as C, C++, Java, etc., there are multiple ways in which an if statement can be ended, or the reign of the if statement can be ended, such as full stop, for instance, and so on and so forth. There are multiple ways in which you can denote. But for clarity, to make the language look like English, we're using a construct which uses end if. Now end if essentially means that the if statement's importance or significance or influence ends there. If we look at both the algorithms shown on this slide, we will realize a very important difference. For instance, the left hand side we show if the guest wants tea, then make tea, end if, which means that if influence has ended there, and offer biscuits, which is after the end if, which means that you offer the biscuits regardless of whether the guest wants tea or not. Therefore, if you see the title, it says offer biscuits to all the guests. If you look at the right hand side algorithm, it says offer biscuits only to guests who want tea. And how do we make that happen? We say if the guest wants tea, then make tea, offer biscuits, and then end if, which means that you offer biscuits only to those guests who want tea. Now let us represent the same algorithm in the form of flowcharts. This slide shows two flowcharts. Left-hand flowchart represents the algorithm that we saw on the left-hand side, which means that we are offering biscuits regardless of whether the guest wants tea or not. If we see this diamond, now diamond is a new figure, new kind of shape that we have encountered, and diamond is the easiest way to actually show a condition. If something happens, then you take certain action. If something does not happen, you take some other action. Here, for instance, you are asking a question. Guest wants tea. If the guest wants tea, then you are making tea. But look at where, after making tea, the arrow joins the main algorithm. The arrow joins the main algorithm, and then you are offering biscuits, which essentially means that you are offering biscuits regardless of whether the guest wants tea or not. Look at the right-hand side algorithm shown in the form of a flowchart. Here the diamond asks a question, guest wants tea, and if the guest wants tea, you are making tea, you are offering tea and also offering biscuits, and then the arrow is joining the main flowchart, which essentially means that if the guest does not want tea, the guest does not also get biscuits. So effectively, if somebody wants biscuits, you better have tea. Let's now go to the next algorithm. We are taking various forms of these algorithms, and the reason why we are taking these algorithms is that the actual programs in real life, written in any programming language, whether it's C, whether it's C++, Java, and so on and so forth, typically have algorithms and data. We're going to talk about data a little later. We are currently talking about algorithms to essentially see what are the different forms that algorithm takes. Now, similar forms exist in programming languages, and therefore we're going to just strengthen our ideas about algorithms, different conditions, different ways to represent different things that we actually do in our day-to-day lives. Another example could be algorithm for offering tea, coffee, and biscuits. In the last example, we had only seen offering tea and biscuits, and we had also seen two parts of that algorithm. One algorithm was for offering tea, offering biscuits regardless of whether one wants tea or not, and the other one was for offering biscuits only if you give tea. Now here we show this algorithm which combines an algorithm for having tea, having coffee, and having biscuits. So let's just go through this. If the guest wants tea, then make tea and end if. So you are giving tea to the guest only if the guest wants tea. Then if the guest wants coffee, then make coffee and end if, which means if the guest wants coffee, then you are giving coffee. And then you offer biscuits. As you know, offer biscuits is after you come out of this end if, which essentially means that all the guests will get biscuits, but those who want tea will get tea, those who want coffee will get coffee. But just notice a very interesting thing here. If somebody wants tea and coffee both, this algorithm will give both, because you are asking a question about tea first, after which you are asking a question about coffee, and then you are giving biscuits regardless. Theoretically or practically, so to say, when we have guests at our house, we normally ask whether they would like to have tea or coffee. We don't ask them tea, and if they say tea, then give tea, and then ask whether they want coffee, and if they say yes, then we give coffee. Normally this does not happen. But this algorithm is in that sense unrealistic, and we have taken this deliberately. If you look at the right hand side, the same thing has been shown in the form of a flow chart. There's a diamond which asks guest wants tea, and yes, then make tea, and obviously offer tea. The arrow joins the main line and then asks guest wants coffee, yes, then make coffee, and then offer biscuits, which essentially means that you're offering biscuits regardless. Now, the next algorithm is offering biscuits only if guest wants tea or coffee. If the guest wants tea, then make tea and offer biscuits, end if. If the guest wants coffee, then make coffee, offer biscuits, and end if. Now, if you see this algorithm very carefully, you are offering biscuits only if the guest is either taking tea or coffee, which means you're asking the guest whether he wants tea or not. And if he says yes, then you're offering tea and biscuits. Then you're asking whether the guest wants coffee or not. Then if the guest says yes, then you're offering coffee and biscuits, and then you're getting out, which means that if the guest does not want either tea or coffee, the guest is not getting any biscuits. But if the guest wants any of tea or coffee, then the guest is getting biscuits. Now there are many challenges here or problems here in this flowchart. Obviously, offer biscuits is unnecessarily repeated. Could we have combined this? Is it necessary to ask question of coffee when somebody has already answered a question about tea in an affirmative? If somebody says, I will take tea, then is it necessary to ask a question about coffee? And so on and so forth. And that makes this algorithm a little unrealistic from the point of view of our day-to-day life. But it will certainly be very useful for us to study this from the point of view of studying how algorithms are written. As we said, let us see whether we can improve upon the algorithm by actually removing a duplicate offer biscuits instruction and asking a guest about whether the guest wants coffee or not, despite the fact that the guest has actually chosen to have tea. This flowchart and this algorithm shows how to remove those shortcomings. Here, if you notice, we are saying if the guest wants tea, then make tea and then go to last. Now what is this last? Last is actually what is called as a label, or last is in fact an address of an instruction. We do not know that actually physical address, and therefore we say last. If you look at instruction number 8 in the same algorithm, you will notice that we have given that instruction a name which is called as last. What that means is, in instruction 3, we are saying that if the guest wants tea, then make tea and then go to instruction number 8, which means offer biscuits. You therefore skip instruction number 4, 5, 6 and 7. Therefore, as you will notice, you are asking a guest whether the guest wants tea or not. If the guest wants tea, then you are making tea for that guest and then going to last and then offering biscuits and then coming out of the algorithm, which means the guest will get tea and biscuits and come out of the algorithm. Let's now see if the guest wants coffee. Let's start from the beginning. If the guest wants tea, then make tea. But in that then instruction itself, the algorithm will not go through that then instruction because the guest does not want tea, and therefore it will come out of endif instruction at instruction number 4 and go to instruction number 5, which will ask if the guest wants coffee, then make coffee. If the guest wants coffee, then you are making coffee. You are coming out of endif and then you are falling through to the instruction number 8, which will offer biscuits, which means the guest is actually getting only coffee and biscuits. The same thing is shown on the right hand side as a flowchart. Let's now trace that through. If the guest wants tea, you are making tea and then again going directly to the instruction which will offer him biscuits and then get out of the flowchart. If the guest does not want tea, then you are falling to the next diamond. In the next diamond, you are asking the guest whether the guest wants coffee or not. If the guest wants coffee, you are making coffee and then offering biscuits and then getting out of the algorithm. If the guest does not want coffee either, which means that the guest does not want tea or coffee, regardless, even then, you are offering the guest biscuits and then getting out of the algorithm. So that essentially is what we had wanted all along. But just notice that we have avoided the guest being asked a question of whether the guest wants coffee or not once the guest has selected tea. And secondly, we have avoided the duplication of offered biscuits. The reason why we're going through the details of these algorithms are these are the different forms that programmers use for reducing the duplication of work. And these are the tricks that most of the programmers actually use while writing programs, regardless of the programming language. Now the only thing that I would like to state here is, there is an instruction at instruction number 3 which says go to last, which essentially says you are jumping from one location to another location. In fact, these jump or go to statements make the program which is called unstructured. Therefore, normally the go to instruction is not used. We have shown go to instruction in instruction number 3 only as an example of how we could save the duplicate instruction or offer biscuits and a few other things. Now let us look at compound conditions with and or. As we know, normally in our daily lives we do not give instructions only with one and or one or. For instance, let us look at this algorithm. If it is a weekday and it is 7 a.m. or more and you are feeling okay, then take breakfast, go to work and end if. So we are putting two conditions here. So please note that only if both the conditions are fulfilled, then you are executing certain actions. For instance, only if it is 7 a.m. or more and if you are feeling okay, then only you are taking breakfast and going to work. So if it is not 7 a.m., let's say it is 6 a.m., then you are not going to not having breakfast and not going to work. Or it is actually 8 o'clock, which means it is more than 7 o'clock, but you are not feeling okay, even then you are not going for work. So which essentially means that both the conditions have to be fulfilled. Let's look at the other algorithm. It is compound OR instructions. An OR instruction means any of these should be fulfilled. For instance, the algorithm says, if it is a weekday, or work is pending, or boss is angry, then take breakfast, go to work and end if. As we know, if the boss is angry, you just have to go to work. So if it is weekday, then you have to go to work, or if the work is pending, then you go to work, or boss is angry, then you go to work, which means that even if it is not a weekday, or work is not pending, but boss is angry, you better run to your work. So when that happens, then you take breakfast and go to work. So this is the algorithm which combines various and or instructions. These are called as compound conditions. There is one more type of instructions or algorithms which we normally encounter in our daily lives, and we also encounter in our computer programs. The reason why we're taking these examples of daily lives is really because we encounter these examples hundreds of times in our daily lives. The important point that I want to bring home is that actually when we converse with somebody, when we talk to somebody, we actually talk to that person in a programming language. We always say if then else, or as we shall see soon, maybe repeat until, or do while, or we give a series of instructions, steps that somebody has to follow one after another, which is called a sequence or selection, and so on and so forth. So basically, we actually discuss, we talk and we converse with somebody using all these constructs. But when it comes to programming language, we start feeling it's very difficult, and the reason why we start feeling it is very difficult is not because it is actually very difficult, but we are made to feel that it is very difficult. In practice, it is not a difficult concept at all. Now let's look at nested conditions. For instance, nested conditions essentially means that we are nesting various if then else. So there is an else that will now appear in our if then statements. For instance, in our earlier if then statements, there was no else. In the nested conditions, we'll now encounter else, which means that if something happens, then you do something else. If something else happens, then you do something else. If something else happens, and so on and so forth. It's like saying, for instance, if you get marks between 80 to 90, then you go to, let's say, Baroda. If you get marks between 70 to 80, then you go to London. If you get marks between 60 to 70, you go to maybe Mumbai. And if you get marks between 40 to 50, maybe you do something else. Now, how do you represent this in the form of an algorithm? If there are such multiple, not just multiple conditions, but if then else statements, then you have to use what is called as nested ifs. Now let's look at this algorithm. If you are feeling okay, then go to work. Else, if you have fever, then go to the doctor. Else, just relax. And just mark now end if. And I think if you want to understand the end if statements, you will need to look up, for instance, the second end if, which means in instruction 8 we have an end if. That end if is for the if statement in instruction 4, which means the instruction 4 to 8 is one if then else loop which ends in instruction 8. What does that instruction loop says? If you have fever, then go to the doctor, else just relax. This is just one loop. Now, if you take the end if in instruction 9, that is for the if instruction in instruction number 1, and therefore they are aligned. This is called indentation. The if then else are not shown in one line, but they are indented. And the indentation, that is the position, is really to show what end if corresponds to what if. And therefore you will notice that the end if in line number 9 actually corresponds to if in line number 1. Or end if in line number 8 corresponds to if in line number 4. Now what is the meaning of this algorithm? The meaning of the algorithm is very simple. If you are feeling okay, then you go to work. Now if you are not feeling okay, then only this else in instruction number 3 will start taking action. If you are feeling okay, then you go to work and then this else does not apply. Then you straight fall through to end if and then get out, which means you go to work. Now what happens if you are not feeling okay? If you are not feeling okay, then you do not go to work, but then this else starts taking action. Else, in instruction 4 we say if you have fever, which means you are not feeling okay. Now you are asking a question, you are not okay, but let's see, do you have fever? If you have fever, then go to the doctor. Instruction 5 says go to the doctor. But if you don't have fever, so you are not okay, but you don't have fever, then you just relax. So you are not feeling okay, but you don't have fever, so not necessary to go to the doctor. Just relax in instruction number 7 and end if, which means you come out of the algorithm. So this is the way the algorithm operates. We need to write this algorithm if we actually intend the person who is executing this algorithm to take actions according to this algorithm. So it's very important to be able to write algorithms in the fashion that we want. Let's take another example of nested conditions. If the guest wants tea, then make tea, else. If the guest wants coffee, then make coffee, end if, and offer biscuits. Now this is a classic example of, if you notice, we had made one attempt a few slides back of removing the duplicate offer biscuits instruction and avoiding a guest to be asked a question if the guest has chosen to have tea, to avoiding to ask a question to the guest to also whether the guest wants coffee or not. In order to do that, we had written an algorithm in which there was go to last instruction, and I had said that go to instructions are not followed. One of the ways to avoid these go to instructions is in fact if then else. These are the nested conditions. In fact, there are three ways in which you can avoid the go to instruction and make the program, which is called a structured program, which means a top down approach, and which is what makes the program good program and a programmer a good software engineer. In early days, when hardware was very expensive and all the programmers, the salaries of the programmers were not very high, all the programmers used to write programs which could save the memory and all the CPU resources, because the same CPU, same computer was used for multiple jobs and hardware was very expensive. So software programmers' aim was to reduce the load on the CPU or memory. In fact, a definition of a good programmer was the one who uses the minimum memory for a program or minimum CPU time. Today, software is very expensive. Software programmers' salaries are skyrocketing. Hardware is becoming very fast and very inexpensive and very cheap and available very, very easily, which essentially means that has changed the paradigm of writing programs. Today, when you write a software program or an algorithm, the main thing that you look at is that the program should be maintainable, because software programmers take up a job, write software programs, then find another job, and then somebody else has to maintain that software program. So the definition of software engineering, or the definition of what makes a good software programmer, has changed over years. What used to be a good software programmer a few years back is not a good programmer today. Earlier, when you wanted to save the hardware resources, you used the go-to statements very often. But when you use a go-to statement, you are following certain instructions, then jumping to some other instructions, then coming back again, then jumping to some other instructions, thereby making the program look like a spaghetti. And therefore, those programs used to be called as spaghetti programs or spaghetti code. Today, in software engineering, there is a term which is called a structured program or structured programming. Structured programming is essentially a go-to-less program, or a program which only falls from top to bottom, which essentially means that if you start reading a program, it never goes to and comes back. So there is no go-to statement. And if there is no go-to statement, then essentially when you read a program one after another, and therefore you make the program far more readable, far more maintainable, and that's the reason today in software engineering it is highly advocated method of programming.